Hi guys, welcome back to the channel. So today we are going to be solving today's lead code question, which is sum to root leaf numbers. So we are given a root of the binary tree, and then we need to find the sum of all the root to leaf numbers. So suppose let's say we are given this particular tree, and then we need to find the sum of all these numbers which are made from this particular root to leaf. Suppose if we take from here to here, then we are going to get 12. Why? Because this will be 1, and then when we go to the next node, we are going to multiply the number with the 10, and then we are going to get 12, and then for this we are going to get 1, and then when we move to the next step, it is going to be 10, and then plus 3, it is going to be 13. So 12 plus 13 is going to be 25. So we need to solve this with some approach. Suppose let's say this is the root we have given, like this is the tree. Now we have 4 and then 9 and then 5 and then 1. So for this we need to write a recursion such that it will solve the problem and then give us the answer. Suppose let's say we'll store the answer in our particular answer, and then let's say this sum is representation of this particular sum from here to this particular node. Suppose let's say as of now we do not have sum, so this will be initialized to 0, and then answer will be 0. Now when I want to move to the next node, which is going to be left, now this particular sum becomes like 4, and then we'll multiply it with 10, so it is going to be 40. And then when we move again, we are going to move to left. So here now it is going to be, we are going to add the 5, and then as it is leaves, we are going to add this particular sum to our answer, so which is going to be 45. So we are going to say this is 45, and then again we'll move from here to here. Here we are going to get the 40 plus 9. So suppose let's say if we move from here to here, this is 40, but again we'll have 9, so it is going to be 949, and then after that we'll multiply with 10, so this is going to be 495. So this is going to be 495, and then we'll add the answer as 495. And then again when we want to move to here, then it is going to be, the sum is going to be 490 plus 1, it is going to be 491. So we'll have the answer as 491. So 495 plus 491, and then again these nodes are completed, 5 and then 1 is completed. Now we need to move from here to here. So here it is going to be 4, and then it will be multiplied with 10, so it is going to be 40, and then again we are going to add 0, so again it is going to be 40. So again if we add 40, then it is going to be, our answer is going to be like 495 plus 491 and then 40. So that is going to be our answer. Suppose if you want to travel this particular binary tree, we need to travel all the nodes which are present in this particular binary tree. So that's why we are going to say the time complexity as big of n. And then if we come to the space complexity, we are not using any extra space, but let's say that we are calling this function, again this function will call this function, and then again this function will call this function. So we'll have a recursive function where we'll have stack in the calling function. So it is going to be big of h, which is going to be the height of this particular binary tree. Suppose let's say if it is a skewed, if the binary tree has only one end, then it is going to be big of n. Suppose let's say I have a node here, and then this particular node lies in the right side, again this lies in the right side, then it is going to be like a linked list, or it is going to be like a array. So that's why we are going to travel all nodes which are present in this particular binary tree. So at that time we are going to say the space complexity is going to be big of n itself. So the time complexity is going to be big of n, and then space complexity is going to be big of n. So let us go through the solution for this problem. So we'll have the answer equal to 0, and then this root to leaf sum will give us the answer for this particular tree, and then we are going to have the sum initially equal to 0. And then whenever we come back to this base condition, whenever we are writing the recursive function, make sure that we'll write the base condition here itself. Suppose let's say it can be some simple valid condition like I equal to 0 or root equal to null, or I is less than 0, or I is equal to s dot size. It can be anything. So this should be our boundary condition or simple valid input which we can put, and then for that what is the answer it is going to be. So for this we are not going to consider any root, so that's why we are not going to add any answer. So that's why we are just returning here. And then let's say um, we have this particular root as leaf node. That means root left will be null and then root right will be null. Suppose let's say we have the node here. Now the root left is null and then root right is null. So that's why we can say that this is a leaf node. So whatever the answer we had got till now, so this is going to be our sum, and then whatever the answer we had got till now, we are going to add it with this particular 5. So that's why we are going to say that it is going to be sum into 10 plus root value. That is going to be our answer. And then let's say this is not the leaf node, this is this particular node. Then we are going to have this particular sum, which is going to be like 40, which is going to be 40 here. Now we need to multiply 40 with 10, and then we need to add this particular value. So that's why we are going to travel root left, and then we are going to add sum into 10 plus root value with the particular answer. And then we are going to travel the root right with sum into 10 plus root value, and then we are going to take this particular answer. And then let's after completion of this particular traversal of the array, we are going to have the answer in this particular answer. And then one more thing we need to take care is, suppose let's say here we are going to have the sum without taking it as reference. Why? Because we need the sum to be different for each particular element, and then we need answer to be same for all the elements. Suppose let's say we add we we add answer equal to 495 here. Now when we call back this particular function and then we get answer here, now when we call back here, then answer should be same for this particular answer as well. So that's why we are going to keep the global variable with the part of reference. Suppose let's say the reference means here I have one bucket, I am just taking the reference of that particular bucket, and then whenever I fill anything in this particular bucket, it is going to be present here as well. So it is just a copy, but it contains whatever the changes will be made to this particular element, it is going to be present in the previous as well. So that is going to be reference and then pass by value and then pass by reference. Here we are taking sum as pass by value, here we are taking as a pass by reference. And then if we come to the time and space complexity, the time complexity is going to be big of n as we discussed previously. And then the space complexity is going to be big of n. Yeah, that's all for this video. Thanks for watching the video.